Welcome to Inorganic Chemistry. In this lecture we'll look at oxidation and reduction chemistry, which can help you with your battery lab and also understanding main group chemistry. We're going to review redox reactions or oxidation reduction chemistry and also review the definition of standard reduction potential and how that can change with the Nernst equation. For new material, we'll look at what's called the solvent window, and then we'll also look at a way of presenting the oxidation reduction information in a very compact, organized fashion called a Latimer diagram. And finally, we'll look at how we can also look at the oxidation reduction information in a graphical format called a Frost diagram. To review redox chemistry, reduction is gain of an electron. And oxidation is loss of an electron. So, as we learned in Gen Chem, Leo goes grr. Here's an example of a redox reaction. One species is getting reduced while the other species is getting oxidized. And so to show clearly which part is going where, we can separate this into two half reactions. The reduction half reaction, in which the copper 2 plus ion gains 2 electrons to form the copper metal. And in the oxidation half reaction, the zinc metal forms zinc ion and loses 2 electrons. Like all chemical reactions, we want to know what's the favored product, and so we're going to use thermodynamics to help us with that. And we can relate the electrochemical potential of a reaction to its Gibbs free energy. So if the electrochemical cell potential is positive, then the Gibbs free energy would be negative, and it would be thermodynamically favorable to proceed. So how do we find the electrochemical cell potential? We look at the standard reduction potential in a table, and that's always presented relative to this definition. The standard hydrogen electrode, hydrogen ions being reduced to hydrogen gas, is defined as happening at 0 volts under standard conditions. So once we know our reduction potentials, we can calculate the cell or the electrochemical potential of the reaction by looking at the reduction of the cathode, the reduction half reaction, what that standard reduction potential is, and subtract it from the standard reduction potential of the half reaction at the anode, which is the oxidation half reaction. Now that's under standard conditions. To find the electrochemical potential under non-standard conditions, we use the Nernst equation. So here we have the standard chemical potential for this reduction half reaction. But then if we change, say, the temperature or change the concentrations of the two species, then we will shift the reduction potential. So this is how an ion selective electrode or a pH electrode works. It measures the potential, the voltage, which will vary based on the concentrations. And here's another form of the Nernst equation in log base 10, taking into account these constants. Now, another thing to consider in a chemical reaction in solution is not just what the concentrations are or the temperature is, but also what the pH is and also what the solvent is, because the species you're working with could react with the solvent. We've already seen that hydrogen ion will react to form hydrogen gas at 0 volts. Water can also do this same reaction. As we know, there's protons in water. So if we add 2 electrons to water, we can make hydrogen gas and hydroxide. This occurs at negative 0.8 volts. What is the difference between these two reactions? There's a different electrochemical potential. One has hydrogen ions and one has hydroxide ions. Oh, we know something about that from acid-base chemistry. Hydrogen ions would be an acidic solution. Hydroxide ions would be a basic solution. And so as the pH increases, our voltage for this reaction should go from 0 to negative 0.8 volts. And that's what this green line here, the slope of this line, is showing, that in acidic conditions, our hydrogen ion will be reduced to hydrogen at 0 volts, but as we go to basic conditions, that voltage shifts negative. What is this line up here showing us? It's the other part of the water, the oxygen part, can also react. As you can imagine, oxygen is a good oxidizing agent. So oxygen will react with electrons to form water. And this occurs at a reduction potential of positive 1.23 volts. So that's right here. And you can see there's hydrogen ions present in this balanced half cell. And so if the hydrogen ion concentration changes, our standard reduction potential will shift. It will decrease based on the Nernst equation. So between these two lines, depending on your pH, is what reduction or oxidation species can be present in water. For chemicals, a strong oxidizing agent, it will react with water to form oxygen. So oxygen is the most oxidizing species that can exist in water. If you have a strong reducing species, it will react with water to form hydrogen. So hydrogen gas is the most reducing species that could exist in water. And in natural conditions, or in the environment, the pH ranges from 4 to 9, so this would be a even more restricted place of stability for redox active species. These orange lines are saying what's called overpotential. And all of this is thermodynamics, but we need to consider kinetics. And that's what overpotential does. It takes into account the fact that this gas has to react with a molecule in solution. Oxygen bonds have to break. All these are different kinetic factors that need to be taken into account. So this increase in electrochemical potential is needed to help push the reaction, and that's called the overpotential. So the solvent window is actually bigger than what we predict by a little bit because of overpotential. But that's what this is illustrating here, the window of stability for a chemical depending on the solvent and the pH of the solvent. Now, how do we find the reduction potential of a particular element? Well, the best way is using a Latimer diagram, because this is organized by oxidation state and also by element and by group in the appendix of your textbook. So if you want to find the particular standard reduction potential for a particular element in a particular oxidation state, look it up in the Latimer diagram rather than your Gen Chem textbook, which listed everything by standard reduction potential rather than by element. For the element manganese, under acidic conditions, the different oxidation states that are possible, that's why I'm showing this, because manganese has quite a range from positive 7 in permanganate all the way to 0 in manganese metal. And these lines here are showing what the standard reduction potential is going from this oxidation state to this oxidation state. Say we want to know, well, what is the standard reduction potential going from permanganate to manganese 2+. The standard reduction potential is this, positive 1.51 volts. And I can figure out what the balanced half reaction is by balancing this transition. We're going from positive 7 to positive 2, so that means we're reducing by 5 electrons. We have 4 oxygens on this side, so we need 4 oxygens on this side. So we'll add 4 waters, and then now we have 4 times 2, 8 hydrogens on this side. So we need 8 hydrogens on this side in the form of hydrogen ions. So that's the balanced half reaction with this standard reduction potential from this line on the Latimer diagram. What if we wanted to know the standard reduction potential for a transition that's not shown on the diagram? So let's say, for example, we want to go from manganese dioxide to manganese hydroxide. There's not a line on this form, and this is under basic conditions. Well, to help us find what the potential for this part would be, we can apply Hess's law because we know what the potentials for these steps are. And by Hess's law, the sum of thermodynamic states is equal to the whole. So, going back to Gibbs free energy, the energy of the reaction going from manganese dioxide, or what we really should call manganese 4 oxide, to manganese hydroxide is going to be the sum of the Gibbs free energy going from manganese dioxide to manganese 3 oxide plus Gibbs free energy going from manganese 3 oxide to manganese hydroxide. So that's Hess's law, and then we recall we can relate Gibbs free energy to electrochemical potential using this relationship. So we can substitute in for all of these. And we know what these values are, so we can calculate this. N is the number of electrons transferred, in this case, going from here to here, positive 4, positive 2, so that's 2 electrons transferred. And Faraday's constant we can divide through here. This negative we can divide through here to keep everything positive. This N here, going from plus 4 to plus 3 is 1. This N here, going from plus 3 to plus 2 is 1. So we're left with 2 times the standard reduction potential equals 1 times our known standard reduction potential plus 1 times our other known standard reduction potential. So 0.15 plus negative 0.25 equals negative 0.10. And that's 2 times that. So divide through by 2 and we get that the standard reduction potential to go from manganese dioxide to manganese hydroxide equals negative 0.10 divided by 2 equals negative 0.05 volts. And we don't write the volts, that's assumed to help make it more compact. Now another way of presenting the redox information is through a frost diagram. So here we have the Latimer diagram, which is very compact and contains a lot of information. The frost diagram plots the number of electrons transferred times the standard reduction potential versus the oxidation state to graphically represent what's happening. So here in the case of thallium, we have on the x-axis the 0 oxidation state, the +1 oxidation state, and then the +3 oxidation state. And we know we start at 0 volts, and then as we go from 0 oxidation to +1 oxidation, we know what that standard reduction potential is here from our Latimer diagram, so negative 0.34 times 1, so we end up there. And then going from +1 to plus 3 is positive 1.25 volts, but that's also 2 electrons, and it's 2, so times that by 2, that's 2.5. So we put that dot there. Now we connect the dots with these lines, and we see there's a negative slope here going from 0 to plus 1. And then there's a big positive slope going from plus 1 to plus 3. This will react to form thulium plus ion. This will react to form thulium plus ion. This is going to be the most stable because the slope is negative here, then our Gibbs free energy is positive for this direction. Now another thing to note is to compare this with what is the Frost diagram of the standard hydrogen electrode. Well, that's actually very boring because hydrogen starting at 0 oxidation and 0 volts going to hydrogen ion plus 1, but the standard reduction potential is 0, so the slope is 0, so it's just a flat line. Since this slope is negative, it's a better reducing agent. If this slope is positive, it's a good oxidizing agent. So comparing the direction and size of the slope tells us whether or not something will react. Let's test ourselves. Does this make sense? Here's the Frost diagram for oxygen. 0 oxidation state, 0 volts, start out. Negative 1 oxidation state, that's hydrogen peroxide, negative 0.6 volts. Water, H2O, is the negative 2 oxidation state for oxygen, negative 2.5 volts. So this slope is steeper than this slope, which tells us that hydrogen peroxide is a better oxidizing agent than oxygen. But we also see that we could connect oxygen directly to water with that slope. That tells us the standard reduction potential going from oxygen to water, which we already saw in a previous slide, divided by N. What we also see is that this hydrogen peroxide is raised up above this slope. So it is actually unstable with respect to oxygen and water. Hydrogen peroxide by left to itself will react with itself to oxidize back to oxygen and reduce to water to form more stable molecules. And this redox reaction with itself is called disproportionation. So, now you have information you need to complete your battery report and also to understand more about main group chemistry.